Hi folks, and thanks for joining me. Happy New Year to everyone out there watching. I hope this video finds everyone doing well during these uncertain times again with COVID. Anyway, when I left off, I had published a video about a airline 62316 from 1936 with a neat little clue that was left behind. It looks like the original owners of the set lived just outside of Portland, Oregon, or in the Portland city itself. And they had bought the receiver, and it was their first piece of furniture. You can reference the split screen here and see what was written or what's written on the bottom side of the cabinet. So anyway, just before the holidays, I had an opportunity to start doing some high-level review of the receiver from the top and bottom side. I'll share that in just a moment. I'm going to piece these videos together, but you know, life has a way of just showing up sometimes, and it slows your progress or your plans down. My dad was hospitalized before Christmas with COPD, and he recovered from that. We were blessed. We got him home on Christmas Eve. So we were able to celebrate Christmas Day with him and my mom and some other family members, so that really worked out well. Unfortunately, just a few days after that, he had a setback and he was hospitalized for pneumonia, which he probably picked up in the hospital, is what we're told. Anyway, since that time, he's back home. Last few days have been better for him, even though there's still some challenges that lie ahead with oxygen levels and still getting the remainder of the pneumonia, 100% cleared up. My mom and I were visiting my dad on New Year's Day, and she took a tumble in the hospital, of all places, which I reckon that's a blessing. And she fell and broke her right hip for the second time. An extended surgery of over 6 hours and recovery. They've got the hip repaired, and she's still hospitalized at this point and will be headed to rehab probably in the next day or so. So a lot of running around on my part and not spending any time really on the hobby. To this point, family definitely comes first. I'm just glad I'm able to be here and help them, during this difficult time. So I've pieced together some videos that I shot, a little update on where I'm at right now with the little airline 62316. So I hope you enjoy what I have thus far, and I'll share more as time permits over the upcoming weeks, or who knows, it could be as long as a month. Everyone out there, take care and stay well. Thanks again for watching. Time to get the dial assembly removed from the receiver, and you can see the little small metal clips and the center dial pointer here. Pretty simple removal, and then a look here at the dial scale. Really cool looking. I may do a little touch up on it along the way. You can see a dial belt had broke at some point. Somebody just placed a rubber band, and it's given up, so we'll replace that. And let me go ahead and get those dial lamps removed so I don't break those, and then we'll look at these 3 fasteners that hold the dial assembly here back to the tuning condenser frame itself. And the 3 fasteners here, a knurled head, kind of a pain to get out. I'll probably go back with a different fastener when I put this thing back together. And just a couple set screws to loosen up, attach back to the stem of the band selector switch. And I was finally able to wiggle this thing out. There's the rubber band, what's left of it. And they're in there a little tight, stubborn, but able to push them out. Those grommets are dry rotted as well. So I'll be replacing those during the restoration process. They've had better days. And a very basic test of the tank circuit itself, and it looks like we've got continuity just using a long wire antenna. You can see I've got the signal generator hooked up to my antenna input, grounding here on one of the cans, and then our signal output off the tuning condenser here back to this first detector tube or mixer tube. I'm in the broadcast band, far left or counterclockwise, and you can see if I rotate here I'm peaking around 521. Again, the loading itself I'm putting on the receiver or antenna coil, pre-selector coil may impact the resonant frequency a bit, but you can see we are tuning for the broadcast band. I should be able to tune 535 to 720 kilocycles. So let me open the tuning condenser all the way open. Change the signal generator here. Alright, let's flip the switch now to the middle wave position. We should be able to tune 1695 up to 5500 kilocycles. Let me leave the tuning condenser where it's at. Change the signal generator here. And you can see I'm peaking right at the, pretty close to the 5500, 5.5 megahertz. Now let's bring the tuning condenser here fully meshed back in. Change the signal generator back down to around 1700. And you can see we're resonant there. So that coil appears to be good. Let's go over to the short wave, full clockwise. We should be able to tune from about 5.2 to 18.3 megacycles, that being equal to megahertz. So we'll leave the tuning condenser here, fully meshed, and let's go up to 5.2. And you can see we can resonate there. Okay, that's opened up all the way. And we should be able to resonate somewhere around 18 megahertz or so. And there we have it. Now if I move the tuning condenser, so I think my tuning condenser is working the way it should, and my guess the coils for the antenna coil, the pre-selector itself, which this receiver has, is working fine. Of course we don't know about the oscillator by doing this test. Still a good indication that the coils, less the oscillator coil, is behaving the way it should be, in addition to the band switch here. You can see if I flip it. Alright, let's move on to some additional tests here, see what we can find. I believe all the tubes are correct for the set, and of course we've got the missing 6F6, which is the output tube. Let's pull these out one by one. This first tube here, the 6C5, that would be correct. That's the oscillator tube. And both tubes here on the front end around the tuning condenser are metal. So that's correct. We'll test these down the road. And the tube sockets are also marked. So 6 Charlie 5 and 6 Lincoln 7. And that's what we have here. 6L7. This is the rectifier tube, or should be. And somebody's plugged in the 6F6 in the rectifier spot. So I hope they didn't apply power. 6F6. And again, the tube socket is marked 5Y3. The 6K7 is what we should have here. And we've got an original Wards Super Airline made in the USA. And definitely the 6K7G. That grid lead here is a little tight. Again, another shield here. And this should be the 6Q7, serves as the second detector. And 6Q7G. And another Wards Super Airline. Possibly the original tubes that were put in back in 1936. That would be cool. 6Q7G here. Tube socket matched. Second detector, AVC first audio. The 6F6, which I said was missing, which was plugged into the 5Y3 socket. That's the output tube. And then we're back to the 6K7 back here, being the IF amplifier. And you can see it kind of makes sense. We've got the lead coming off of the IF transformer back to that tube. The rectifier tube here, the 5Y3. That's pretty cool. They don't have it sitting right on top of the power transformer, but the 6F6 generates a lot of heat as well. Draws the majority of the current in the set itself, aside from the rectifier tube. And I mentioned the 6L7, the mixer tube, first detector. And the giveaway there, you can see the lead coming off of the tuning condenser, attaches to the grid, and the 6 Charlie 5 for the oscillator section. Alright, let me set the tubes off to the side, and we'll test those down the road. Pretty cool. I've got the original solar capacitors still here on top. They're probably dry electrolytics. Possibly restuff those. If not, we'll just mount new electrolytics underneath, like someone has done over the years. Power transformer's a little loose. Hope that's not a sign that somebody pulled this thing out for a problem. Let's do a little testing now on the power transformer. Take advantage of the tube socket adapter here. Plug it in the 5Y3. We'll check between pins 6 and 4, the two plates. And we're reading 518 ohms. I've already identified the center tap location here using another tube socket adapter. Let me get plugged in here. You can follow along on the schematic. Again, back to pin number 4, which is plate number 2 of the 5Y3. So we're approximately 1/2 of the 518, and we'll go back over to 6. read there, add those up, and we're within about 6% on both of the windings, so under 10% is what you want to see. So I think we're going to be fine there. Let me get over to the primary side. Let's bypass the faulty switch, or what I believe to be a faulty switch. Okay, looks like we're settled in 13.5 ohms of DC resistance. Let me grab the little 9-volt power supply. Let's hook it up, extrapolate what we think the high voltage will be, do some calculations on the transformer just for giggles. Bypassing that faulty switch here, let's plug in the transformer. So 61.8 volts AC. Let's look at the center tap back to the plate. 6 to center tap, 30.8 and 30.9, balanced really well, so we know the number of turns per volt is accurate for the transformer. Alright, let me get the wall wart plugged in here. Look at the primary voltage under load, 11.72. 11.72. And taking some time here to document the number of fasteners that were used to hold the tuning condenser in place, in addition to the grommets, the placement, and how many and what size, just so I can replace those during the restoration process. In addition, the lead dress and documenting the terminal locations, so we make sure that I get this thing back together correctly and don't have any surprises with the oscillator section, the antenna section, and or the pre-selector section of the tuning condenser itself. It's quite interesting. Felt was actually used instead of rubber grommets in many of the locations for the tuning condenser. Not sure if that was done from the factory itself or maybe later replacements that were done. You can see the tuning condenser removed, and it's time to do a little basic test. Just looking at the capacitance of each section, just so we've got that documented. Then I'll remove the mica pieces and give this thing a bath. And a quick look at the top of the chassis after getting the tuning condenser removed. Not much rust to remove at that point. And after soaking the tuning condenser overnight in some citric acid and water and a nice rinse off, and then numerous cycles here in the ultrasonic cleaner, and then a final rinse off and dry. So it really turned out rather well and looks a heck of a lot better than our starting point, that's for sure. And after cleaning the mica pieces with alcohol, getting those reinserted into the tuning condenser, and then revalidating the capacitance per section just to ensure we don't have any shorts and or open and everything's performing well. So picking up where I left off, you're looking at the primary winding again where I used my transformer. We applied 11.72 volts, and you can see on the secondary high voltage winding we read 61.8. So I can take the 61.8, divide that by the 11.72, and calculate the turns ratio. Again, not the turns per volt, but you see we come up with about 5.3. And if I use the voltage called out on the schematic itself of 119 for the line voltage, multiplying the turns ratio of 5.3 roughly times 119, brings me back to a full high voltage of around 628. again, the radio itself will only use 1/2 of that. Since it's a full wave rectifier, we'll divide that by 2. So, a realistic estimate would be 314-0-314 for the transformer. Again, just an estimate, that being unloaded. If you look at the top real quick, and we'll look at the voltage divider math in just a moment, but I've laid the tubes out for the receiver and pulled all the specs for the plate current and the screen current for each of the tubes, rated at 250 volts. According to the schematic, this particular receiver operates around 200 volts, B+. So you can see the total current consumption at 250 for the tubes is laid out right at 67 milliamps. But again, with a reduced B+ voltage, the current will be less. So I'm estimating somewhere around 54 milliamps. Probably a safe number, 54 to 60 milliamps. Once we get this thing, lit back up, time will tell on that. Let's look at the estimated plate-to-plate voltage for the 5x3 under load, and then stressing the transformer as well in there based on some of the math that we've done in the past. And then we'll look again at the voltage divider math. Again, one method to estimate the plate-to-plate voltage for the 5Y3 under load, we can take that 628 that we extrapolated here, using the turns ratio times the line voltage input. So 628 minus 2 times the 518 ohms, that's the DC resistance of the high voltage winding, times the current. Again, I'm using the 5 point roughly, or 54 milliamps of current roughly. Again, just an estimate. That number could be higher. Then we can take the voltage, 628, minus, again, the 2 times 518, times the current, and we can calculate what we think the voltage would be off of each plate, somewhere around 286 volts or so. Again, that number's going to be off, a few percentage points, but that gives us a ballpark number to work with. Just below that, looking at the math for the transformer itself, we can take the 628 volts divided by the 518 ohms. It gives us that voltage to resistance ratio. And again, just looking at my transformer I used in the past, taking one to the absolute max, I came up with a constant of 46.5. So really stressing this transformer, you can see I'm showing about 56.4 milliamps, again for the B+ current. As I mentioned, only an estimate of the transformer rating. Let's look at the voltage divider math at this point. Okay, you can see I took some time here to redraw the schematic itself. Just a hand drawing, again from the rectifier tube back, has called out 200 volts B+ voltage across that 8 microfarad capacitor there, number C15. And here's our voltage divider network, again back down to ground. And you can see we're coming off the center tap of the transformer, and doing so allows us to use the voltage divider again as the bias for the tubes. So we're able to bias all 3 tubes in this case. The field coil at 1550 ohms, and then R12 at 220, R13 at 32, and R14 at 52 ohms to ground. Again, I can use these numbers, and the reference is called out on the schematic as a starting point. Again, we know we've got 200 volts is called out on the schematic itself for the B+. And you can see at this point they were calling for -3 volts off of this particular location of the voltage divider. You can see I can total the resistance here, as all the resistors, including the field coil, are in series back to ground. So we've got 1854 ohms as a starting point. To calculate the current, I can actually take the -3 volts, and I could do this in negative and or positive, divide that by the percentage of the DC resistance that 52 is of 1854. So if I take 52 divided by 1854, you can see it's about 2.8% of the total voltage divider itself. I can divide -3 again, divided by the 0.02805, and that gives me 107 volts. So we're going to drop or take away from the B plus 107 volts, and I think that's going to get me fairly close here. So if I make -107 my starting point here, on the input side of the field coil, we can do the math for each section of the voltage divider and calculate the voltage drop that way. Just a way to back into it. So let's work through that real quick. So working the math backwards again, if we take the 0.02805 times 107 volts, you'll see that we come up with 3 volts, and or -3 in our case, from center tap back to chassis ground. So that's this point here. If I take 52 ohms and 32 ohms, which would be 84 ohms, and divide that by 1854, you can see the percentage would be equal to the percentage across the 52 ohms and across R13. We can sum those together and multiply that by 107, and you'll see that the voltage drop at this point is -4.85. The same thing for the next section here. I can add the 0.02805, the 0.017259, and the 0.11866 together, times 107, and back into the -17.5 volts at this point, back over to the 6F6 output tube. And you can see across the field coil 0.83603. Again, all these added together will equal 1. So again, in conclusion, one estimate showed just under 3 milliamps of current, and this method brought me back closer to 58, so probably somewhere in the ballpark. Again, I'll be off a few milliamps probably either way once we bring the circuit back up, but I think this gives you a general idea how to back into the numbers for the voltage divider using some simple math and leveraging Ohm's law. So you guys take care and stay well. Thanks for viewing.